So my name is Mark Duffield, and I'm the worldwide tech lead focusing on semiconductors for AWS. And speaking with me is Simon Burke, who's standing off to the side here. And today we're going to cover scaling EDA workflows on AWS. So really what I would like to do is go over some of the details of building out architectures on AWS with respect to EDA flows and with respect to the semiconductor industry, and really set it up for Simon. So the idea is really to have Simon dive into his architecture and really have him walk you guys through his journey, where they're at with their architectures and some of the next steps, and some of the problems and some of the things that they've seen along the way.
So Xilinx, first of all, my name is Simon Burke. I'm a CAD architect at Xilinx. My job is to take a great idea and evaluate whether it actually works and then turn it into a production flow that our design team can use to tape out chips. The end goal is to tape out chips. That's what pays the bills, so that's kind of what my team does. If you haven't looked at FPGAs in the last 10 years, I would encourage you to go look at the Xilinx website and see what we do. 10 years ago, you either knew you wanted an FPGA, you knew all about them, or you didn't know what they were and you didn't care. Today's FPGAs are really systems on a chips. We have GPUs, CPUs, hardened DDR controllers, PCI Mac controllers, lots of hardened IPs, network on a chip. It really is a programmable system on a chip today with some FPGA that you can use as well, compared to the field programmable products that we had 10 years ago. So if you're not sure what FPGAs are today, go take a look. You'll be surprised, I think. So in terms of how do you do this, first of all, if you want to say, I want to run the cloud, what do I need to go do? I would say that probably the biggest issue that you'll find is as you run stuff and as you start to evaluate whether you can move a flow to the cloud, you will run into problems. It's not going to be just plain sailing. When you run into those issues, it will not be clear whether it's an EDA tool problem, a fab problem or a tech file problem, your internal flow, or whether it's something to do with Amazon. And what you'll find is there isn't one person in your organization that has all the knowledge of all of those domains in their head that you can go ask what's wrong. You will end up having to coordinate between those different groups. So getting a good program manager that can go do that and getting the right people in those companies together so you can go figure out where a problem is essential, otherwise you just won't make progress. So yes, having that coordination is something you will need. Just plan it up front. Don't wait until you need it. You will need it, I can guarantee it. In terms of how to use it, this is kind of some background stuff for you to understand what use models are. Different people have different definitions. These are mine. Really, I see three different use models for the cloud in my peers and other companies. First is the all-in model. It's very common for smaller startup companies to go do this. Some of the EDA vendors also provide a cloud service, which is really an all-in model. What it means, you move the storage, the compute, all the infrastructure onto the cloud. You run entirely on the cloud. And when your job's finished, you tape out the chip from the cloud. From a technical perspective, it's probably the easiest environment to set up. And there are a number of companies out there that will give you a turnkey solution that you can go pay some money and they'll just make it all work for you magically. So technically, that's the quickest path to get running on the cloud is the all-in model. You will find for small companies, it's a great option. Medium and larger size companies, Xilinx will be one of those. It's seen as a risk to put a whole product on the cloud in an entire environment that you didn't know anything about before. That is perceived as a company risk. So whilst it's technically easier to do, the profile risk is considered to be quite high. Somewhere in between is a hybrid model where I have 12 projects. I'll run 11 of them on-prem in my traditional flow, and I'll move one of them onto the cloud and see how it goes, a test vehicle kind of thing. You can pick the low-risk project that if it slips a little bit, nobody really will care too much and see how it goes. So it's really the all-in model, but in a smaller scale. And again, a lot of companies will do that to kind of put their toe in the water to see if it works and what happens. The burst model is the one that's technically the most difficult to implement, but has the lowest perceived risk from a corporate perspective, and that's what Xilinx is doing. Burst model says, I want an infrastructure on-prem where I can run my jobs, and when my capacity on-prem is exceeded or maxed out, I want to overflow into the cloud. Some of the constraints there mean that the flow that you're running has to work on the cloud just the same way as it works on-prem. You really don't want to have a different flow on the cloud to the on-prem flow. The CAD team will hate you forever. Don't do that to them. It does mean that you have to make the cloud environment kind of look like your on-prem environment to some extent, so that your flows see it as the same world that they're running in. The other issue is data storage, is how do you get stuff from on-prem to the cloud in time to run the job and then get it back in afterwards. So there are some technical challenges there. Makes it more interesting. However, from a project risk perspective, it's probably the lowest risk that the corporation will see, because ultimately it just says, well, if it doesn't work, I'm just maxed out on my internal farm and just continue to run maxed out. My jobs will end, but they will run and they will finish. So you do have a easy fallback plan, which is I'll just run it on-prem the way I always used to. So there's a different risk and technical challenge aspect to those three models that it's worth considering before you dive in. And as said, Xilinx has chosen to pursue a burst model. The upside for us is if we can make burst work, we can also make the other two models work because they're subsets of burst. So you make that work and everything else just kind of falls out of the pie. So there's some good and bad about working on the cloud. The good side, which nobody really talks about because it just works and it's magical and it's fantastic, is the networking on the cloud is awesome. It's fast, it's reliable, it just does what it's supposed to go do. It's way better than on our on-prem network, in my opinion, but it's reliable. It's what Amazon does every day, and they make it work well. Their compute is also generally better than what you'll buy on-prem. Typically, when you buy servers, you have a lifetime of 2, 3, 4 years, take your pick. So you've got a mix of 1-year-old, 2-year-old, and 3-year-old servers in your farm. And if you happen to get the 3-year-old server, it's going to be slower than the 1-year-old server. It's just the way it works. You go to Amazon, and they churn their hardware over much quicker. You get really fast servers. So in terms of just pure compute, you can expect traffic on the network to be quicker and execution to be generally quicker because their CPUs run faster and they have a lot of them. So those two things work really well. The challenges are really around, in my opinion, storage and cost. Storage, as Mark mentioned, there are a couple of options on Amazon. EBS is reasonably fast. However, it's not a shareable storage, it's assigned to a single instance. So it doesn't look like an NFS mountable drive, which is what most of the EDA flows are expecting. Most of the Amazon instances, the ones you would use anyway, also have NVMe drives on them, which are super, super fast, but again, only accessible to the instance that you're running on. So if you can localize the job, great. But that isn't the way most of your EDA tools will have been written that run on-prem, and they want to run the same as on-prem as on the cloud, so not an option. EFS is shareable across multiple servers, and it has some performance challenges. You can see a very significant degradation in runtime performance running on an EFS shared drive compared to your on-prem NetApp or wherever you use. FSX Lustre is something Amazon has been working very hard on to address this gap. It kind of fills in the gap between EBS and EFS. Again, there are some trade-offs there in terms of how you enable it and roll it out, but it addresses a lot of the technical issues, potentially. The flip side of storage, though, that you have to bear in mind is cost and security. You are putting a large amount of data on the cloud to run your jobs. For us running a typical VCS job, because our flows were not written to be efficient on the data they read, it's just like the data's on the LAN. I can get to it anytime I want. So you pick little bits of data from all over the place on multiple file servers. It has a very large footprint of data that it wants to see to run. My single VCS job requires today close to 200 terabytes of file system to be available for it to run. It's not reading 200 terabytes of data, it's reading about 1% of that. But it needs that file system to be available to run. You can go figure out which bits and pieces in the file system you need and just copy those over. But that's a really tedious task to go do, and you don't get to do it once. You get to do it every single time, because the 1% of data that's reading is a different 1% each time. It moves around just slowly, but it moves, it wanders. Keeping track of it is just a real pain in the ass. So there is that aspect to it, and just storing 250 terabytes of data on an Amazon environment permanently there's a cost associated with it. Go look it up, you'll figure it out. It's more than I can afford. The other aspect of it, which is a perception, not a reality, is around security. In general, my opinion is that the data security on the cloud is as good or better than you have on-prem, simply because on the cloud you can limit who has access to the data more than you can on-prem. You can set it up so only jobs that go through a queue go to the cloud and people don't log on and your data's secure. But there is a perception amongst all of your engineers that it's insecure because it's not on premises anymore. You can spend an awful lot of time talking to those engineers about how that's not true and try to convince them. Eventually, you just fall into the fake news bucket. Nobody believes you anymore. Or you can just tell them it's ephemeral. The data's only there while the job's running, and it goes away afterwards. It's a much easier argument to have because then you just move on and go out and have lunch and hopefully get some beer. So storage is tricky both from a technical perspective and I wouldn't say real security. It's the perception of security, which is a real problem, but slightly different from real security. I also say storage falls into two broad categories. There's the large semi-static read data. There's tools, it's binaries, it's IPs, it's views, it's all that kind of stuff. It's typically a very big file system, but very sparse access. And then the actual workspace data, where the job's running, you tend to get a very lot of read-write access to that particular small space. And if you're running a lot of jobs in parallel, they'll all be trying to bang on the same kind of file system. So you do have these two very different workspaces that you have to go deal with. For Xilinx's perspective, we've used a system called PeerCache from IC Manage to address this. It has a couple of features that we like. One is it's a virtual file system, so that when we turn it off, all of the data on the cloud disappears. So it's ephemeral, which addresses some of the security concerns that we have. It's an on-demand pull, so when someone requests a block, it gets copied from Xilinx Prem into a local cache and gets served to the application. It's block-based, not file-based, and that's actually a big difference for EDA flows. EDA flows tend to read small sections of large files quite often, so copying over just the block it's reading as opposed to the entire file does make a difference to the performance. And the other thing is it uses the NVMe drives as the cache mechanism, which are essentially on the EC2 instances that you already have, so they're free, which means you're not paying an extra storage cost somewhere else on the side. It's already on the machine that you're already paying for. And it's ephemeral. When the instance goes away or when the job finishes, the data disappears. So that's the solution that we've chosen to pursue. It's not the only solution, it's just what we're using. So I would say just from a storage perspective, computer networking, very good. You do need POSIX space file management, and that can be challenging for hybrid and burst use models specifically. So you do have to figure out how you're going to address that problem up front. And again, it will fall into two broad categories. There's these large semi-static read data and smaller dynamic workspaces, and they have very different I/O profiles and requirements. So you may choose one storage solution for one type and a different one for the other type. So consider those two separately. They're not the same category of problem to go deal with. So again, we're using the same virtual file system for both semi-static workspace storage and the large and the smaller dynamic workspaces. It does work for us. It is a different use model, but I would look at all the solutions in the context of those two different namespaces and decide which one works for you. So storage is one thing that, in my opinion, is a challenge on the cloud today. Something you're going to have to think about and decide what works for you. And I've talked to a number of peers in the industry who are doing cloud enablement that's similar to Xilinx, and I think they're all doing something different. I don't know of any one company that's doing the same solution, so there is a lot of subtleties in there in terms of what works for me. I would say there's also not very good visibility into what all the solutions and options would be. The other key area beyond storage is around cost management. And you'll find that Amazon has a lot of infrastructure and tools to tell you what the bill is at the end of the month. And you can go tell who spent the bill and where it all went and profile it up the Yazoo and produce nice charts and all that good stuff. But at the end of the month, you still owe them money. And one of the things that I received a lot of pushback from my design team is they wanted to do proactive budgeting, not retrospective paying the bill, which means that they want to allocate a budget to certain teams and flows and say this is what you're allowed to spend that month. And when you've got to that limit, you are not allowed to run on Amazon anymore unless someone changes the budget. And then at the end of the month, we go ask Amazon how much should we spend, and we reconcile it all and make sure it all adds up. So what we do, and again, this fits in nice with the burst model, which is when a job is submitted, well, first of all, we ask, is it eligible for the cloud? Can you run the cloud, or is it just a flow that we haven't qualified yet, so you get to run on-prem? If it is eligible for the cloud, the first thing we ask is the on-prem queue full? Because if I've got machines sat there doing nothing and we've already paid for them, you might as well use them because it's free. So if we have capacity on our prem, we just run the job there. If the internal queue is full or close to capacity, or there's some other limitation that means we don't want to run on-prem, then we go ask if that user or the group has budget to run on the cloud. If they've already exceeded their budget, they don't get the option. It just goes on-prem, it sits in the queue, they pend, they go talk to their VP, he goes and talks to finance and gets more money and puts in the budget. The last one is, and this is important in terms of how you do the prediction. We have a profile database that keeps track of previous jobs, and we use it to predict how much a job is going to cost. When a job gets submitted, you don't want to find, do they have enough budget, but do they have enough budget including the cost of this job? And then we adjust the budget with the predicted cost of the job immediately, and then let the job go run. That means when the second job comes in, the budget's already maxed and they'll redirect to on-prem. When the job is finished, we go find out what it actually costs as opposed to what we predicted, take away the predicted cost, add the actual cost in, and then we have a new budget. What that means is you end up with a little bit of noise in the budget number. It's accurate to 1 or 2% in a point in time and figures itself out over time. So there's a little bit of noise in there. It doesn't mean that we can approach the actual budget number we apply. It may go over by 1 or 2%, but then we can lock it off and that group gets to run on-prem from that point on. So costing is important. We didn't find a good third-party solution to this. Everyone was willing to tell us what the bill was after the fact, after we spent the money. We didn't have a good way to do this up front. What we did do is we created our own solution for doing cost prediction and cost management. And we intercept, in our case, we use LSF, so we intercept the B subcall to decide where the job goes. And depending on whether it's a thumbs up or a thumbs down, it goes to the cloud or it goes to on-prem. So there's some other considerations you got to be aware of. Security, I don't think it's really a showstopper issue today. Security on the cloud is very good. All the companies I've talked to that have been doing the same thing as us, had their ITs audit the cloud security environment and come up with a thumbs up that says it's good enough. So from a realistic perspective, security is not an issue. There can be a perception of a security issue versus a real one, and that can be just as problematic. But in reality, security is not a showstopper issue today. EDA vendor licenses, even when the EDA vendors say, yes, we'll allow you to run the cloud, just getting your licenses modified or your legal agreements modified to enable you to do that can take an inordinate amount of time, even when everyone agrees that that's what they want to go do. So yes, you would need to plan that up front and start talking to your EDA vendors about, can I do this? The way Xilinx does it is we host all the licenses on-prem on an on-prem server. We access them via our connection to the VPC, and pull them into the cloud that way. It does mean that we have to have amendments to our legal agreement that says any license that we host on-prem for a certain vendor can be run on the cloud as well. It takes time, go do that. Similarly with IP vendors, they get very nervous when you say, we're going to put your IP on the cloud. They want to know, did you do a security audit and blah, blah, blah. And then the thing that really takes time is modifying the legal agreements to say you can go do that. Lawyers have no rush about them. They see rushing as a risk and they don't want to. So EDA vendors and IP vendors are the two that you need to do up front. Again, become best friends with your IT organization and the cloud vendors. You will need them, I can guarantee it. Take them out for beers, buy them coffee, do whatever you need to go do, but you want them to be friendly too, otherwise you just will fail. And I hear a lot of people saying, we go to the cloud to save money. I don't think that's true. Moving to the cloud is not a cost-saving exercise. If you're going into it from that perspective, don't waste your time, don't bother. What it does is it gives you agility and scalability. And to put that into context specifically, the problem that we have all the time is, obviously you get to the back end of a project, you're trying to get close to tape out, you get surprises because it's engineering. It's the other synonym for engineering is be surprised. So you will find you'll have to do additional runs and additional verifications that you didn't think you had to do before. You didn't plan for it, it just comes up. You can go to the EDA vendors and get peak licenses from them and have them on-premise same day. Super quick, especially if you organize your EDA contracts appropriately. So you can get licenses to run the jobs very quickly. What you can't get is a machine to run the damn thing on. It can take you easily 2, 3, sometimes 4 months to get a batch of service in, plumbed into the farm, configured and ready to run a job. Typically that's way too late. So you end up in this unfortunate situation of having to predict hardware needs to deal with surprises when you don't know what the surprise is. And if you could just say, I'll buy one type of server and it'll cover all the flows, it doesn't work either. Some flows want a lot of CPU, some want a lot of memory. You don't get the two of them together. So you have to know what type of hardware to go buy. Where the cloud will give you a benefit is being able to get peak licenses the same day, and then be able to burst overflow into the cloud on peak hardware the same day. That's the agility you get, is to mitigate a tape-out slip. Not even to pull tape-out in, just to stop a slip happening. And it isn't going to save you money, it's going to save you any costs anywhere. It's going to give you the ability to not slip a tape out and to manage your schedules the way you originally intended. That's the benefit. Ain't going to save you money. If you do save money, that's great. That wasn't our focus, our goal. So just to summarize what we are doing, our use model is burst. We are using ICM PeerCache virtual storage for both the semi-static and the workspace data. Typically for our compute, we use C5Ds for the default server, and we use Z1Ds when someone says, I want a turbo button and I want it to run faster. They do cost more, they do run faster. Our experience is they're around 5 to 10% faster and around 30% more expensive, so there's a premium to get the 10% faster. So don't make it the default. We don't make it the default. We make it the, you should know what you're doing when you ask it for, because as a user, you're going to go pay the bill. Z1Ds give you a reasonable amount of memory, but you do find a lot of EDA flows today kind of settle around the 512 gig or 640 gig memory footprint. That's kind of what they want at the SoC level. Those don't fit in the Z1 family, so you end up going to the R5s or the X1Es. R5s are really good for larger things like SDA, and the X1Es are really good for things like EMIR and the larger physical flows that just consume gobs of memory. So you'll use a range of instances. You just have to go figure out what flows map to what instances and how to go do that. Q, we use LSF, including LSF Connector for instance creation and cleanup. I would say it's not perfect. There is no perfect queue. All the queues that I've looked at today were developed on-prem for use on-prem. They do work on the cloud, but they weren't designed to work with the cloud, so they have limitations that you've got to be aware of. Particularly tracking runaway instances, they can rack up dollars very quickly, and they're kind of transparent. They just kind of sit in the background and ghost your bill. So there is some stuff you have to go do to track those kind of issues. I do want to do a call out to Altair's network compute. They've been doing an awful lot of work on their queue to optimize it for cloud usage. I think that's the only one that I've seen them doing a lot of R&D in that direction. We don't use it today. It's something we are looking at, so I think that looks promising. Network, within the cloud, you just use the cloud's network. It's good. We spent an awful lot of time looking at how do we get from Xilinx to the cloud, and there really are a couple of options. One is VPN over the internet, and the other one is Direct Connect. Everyone wants to use VPN because it's easy and it's simple and it's cheap, and it doesn't work. It almost works, which is the annoying part. The problem is the latency that you get. EDA flows tend to be very latency sensitive. They were designed to work on a WAN. They got stretched to work on a LAN side. They got stretched to work in a WAN environment. They don't like working where you got latencies that exceed typically 500 milliseconds to a second. If you use a VPN, you'll see latencies. We've seen latencies all the way up to 30 seconds. It doesn't happen very often, but they happen often enough that you will see an issue for it. And they're a pain in the ass to debug because you see an odd issue happen every 2-3 days. I've talked to some other companies that have been having the same kind of issues and the same kind of results. So a Direct Connect will cost you more. It's more difficult to set up. Your IT team will hate you for it. It's what I would recommend you go do. Licenses, we host on-premise and we serve to the cloud. You have to be aware of what type of job you're running when you go do that. We have seen some flows that just work fine. We have some spice jobs, for instance, that run really quickly. They're typically in the 2, 3, 4 second range. The time to get the license exceeds the runtime, and your overhead becomes significant when you go do that. And I'll show you some data results later that highlight that problem. So yes, in general, we run on-prem, but I can see certain tools where you'd also want to host them on Amazon as well. EDA vendors don't allow you to do duplicate licenses, so you got to split your pool, 80% of them on-prem, 20% on Amazon, and do cross-referencing so that when one runs out, you get the other one. It's kind of a pain in the ass, but it works. Architecture-wise, cartoony diagrams so you can kind of see what we do and how we do it and why. So typically on the Xilinx side, we use PeerCache as a holodeck server that looks at all your NFS file systems and packages them to be sent across to Amazon. We also have a number of MongoDB and SQLDBs that stay on our side. And typically we use NetApps for our NFS file service, and those feed into the PeerCache holodeck. On the Amazon side, we have a PeerCache tracker, which is the first level of cache that provides the virtual file systems. The second level actually runs on the compute instance itself using the NVMe disks as a cache and exposes the file systems on those as essentially they look like they're NFS-mounted file systems to you. You can look at them, LS, DS, cat files, et cetera, et cetera. We also have a couple of, we use ICManage as our database server as well. So we have a proxy server that we run there just to do some caching to offload any network issues between Xilinx and Amazon. You will get variability. It's good to hide some of that with caches if you can. So that's really what we do. In terms of how much do we push up there, it really depends on the type of job that we're running. We categorize our jobs. Most EDA flows tend to be memory limited more than number of CPUs limited. The job says, I want 512 gig of memory. They don't say, I want 12 CPUs. So we categorize our jobs by memory footprint. Our defaults are C5Ds for kind of the small jobs. We do use R5s for stuff that requires 512 gig and 640 gig. I have R4 in here. We've moved to R5s for the larger footprint machines. And we also go up to X1s for the stuff that's a terabyte and higher. What's interesting to what we do anyways, we look at the spot cost versus the on-demand cost ratio. One of the issues with Spot is, the good thing about Spot is it's way cheaper than on-demand, so you can save a lot of money. The downside is Amazon can go take it away when they want it. What you want is a Spot machine that you can keep for as long as possible. And if you go ask Amazon, what's the keep rate of these things? They either don't know or they won't tell you, or both. What we have observed, though, is where the Spot cost is low compared to the on-demand cost, Amazon tends to have a lot of those machines, and we tend to lose them less often. So we look at the Spot versus on-demand ratio, and when that falls below 20%, we'll say we'll use them. When it's above 20%, we typically don't. That's just a gut feel, pull the number out of my ass, and feels like it works for us, but it's what we do. Also, in terms of workload, we have this little kind of 4-quadrant chart that we have that says what the job restart cost is versus the duty cycle. Job restart cost really is if you're running a 48-hour job and it dies in hour 47, the restart cost of that is really quite high. You've got to restart it and wait another 48 hours to get your answer. Kind of pain in the ass. If it's a 1-hour job and it dies 3/4 of the way in, you're only an hour away from getting the result, you just restart it. So low on the left axis is really short jobs. High on the left axis is very long jobs that are expensive to restart. Restart cost is not just time, it's also the cost of the license that you're consuming to rerun the job. Duty cycle is a little bit more vague. Duty cycle is how frequently or consistently you run this job over a period of time. If you were to look at running EMIR, for instance, at the full chip level, if your project lasts a year, you're typically only running that for about the last 2-3 months of the project. The first 3/4 of the year, you're running smaller blocks. They don't need that size of memory footprint. It's only when you get to the end, when you're on the full chip, where you need that memory footprint. So if you're running 3 months out of 12, your duty cycle is 25%. Whereas if you're running consistently through the entire year, like if you're running block level SDA, that's 100% duty cycle, you're running all the time. So if you do duty cycle versus job restart, you'll see that the top right corner, where you're running the jobs constantly all the time, and where the cost to restart a job is high, you just run it on-prem. It's the safest thing to go do. But as you start looking at the restart cost, okay, if in the machine when it got taken away from me, I can just run the job. When that falls down to a certain threshold, it makes sense to run Spot instances. You can afford to lose the machine and not kill yourself from an overall productivity perspective. And then there is this other category, which is the upper left, which is, yes, the restart cost is high, but we don't run them very often. Full chip EMI is a good example of that. There you can do on demand because you're guaranteed to keep the machine for the duration of the run. And you're not using it for the full 12 months, it's only for a short period of time. So that little chart will tell you kind of what type of instances to use where. So the problem statement for us is really, we want to run using the Amazon environment, but we want to run using our internal flows as much as possible. We have targeted VCS as the initial target because that's the thing that peaks on our queue most often, and it's a natural thing to move over. We're also interested in back-end flows. Synopsys Primetime and HSpice is one of the flows that we targeted to go look at and use. I'm going to skip over the problem statement. Suffice to say that time capture within Xilinx is not a traditional SDA run that you would normally see in an ASIC world. It's more like critical path analysis. We have to capture the delays on a bunch of net segments and feed them into our database. So it looks more like critical path analysis than regular SDA, which means we actually do a lot more runs. We also use Altair's flow tracer tool to manage our flows. It makes seeing what's going on a little easier for us to track. Each little box corresponds to a job or a task. Whilst we currently run Altair on-prem, we don't run it on Amazon. We do have some of those boxes that will push those sub-jobs into the Amazon queue, and then in general pull the results back. So in terms of what do we see? If you run something like Primetime just screams on Amazon. I don't know why. I'm not going to complain. I'm just going to take it and say thank you very much. But yes, what would take us 61 hours to run on-prem, we can do in 34 hours on Amazon, almost 2x speed up. And it's a combination of network and I/O read time and just compute itself. Spice went completely the other way. What took 61 hours on-prem took 115 hours on Amazon. And this is because we run a huge number of really small jobs. The jobs are typically 3, 4, 5 seconds. The time to get the license from the Amazon premise and bring it back before the job actually runs is a significant part of the Amazon runtime and not on-prem. So you see it slow down, which means that for a 5-second run, it can take us an extra 5 seconds to get the license. It will take a little bit. I've broken it down by PT on-prem and PT Amazon, so you can kind of see that how you run the job and what type of job it is also is variable. The speed up is not just 1.9x, sometimes it's parity and sometimes it's much faster. What you're running and how you're running it does make a big difference. And in terms of test cases, we tend not to run the entire chip because just capacity won't fit in the memory footprint, and cloud vendors tend not to have very fast, large memory machines. What we actually do is this MSOC flow, we call it, where we shrink down the size of the design by pruning out just the parts we care about until it'll fit in the memory footprint, then we run that on the cloud. It's a more efficient way of running on a fast server. Correlation, do you get the same answer? Yes. We ran it there, we ran it at Amazon, we ran it on-prem, we compare the numbers. They're within the noise floor that we would expect, so yes, the data comes out the same. Correlation's good. So from just a high-level conclusion, we are currently supporting VCS verification flow in burst mode on Amazon. Our goal, though, is to be able to take an on-prem flow and run it on the cloud without significant changes to the flow, just as it is. What we do see is every time we transition and run a flow, we do see issues, and we have to modify the environment a little bit to work with that. Those modifications are not in the flow, they're in the environment underneath the flow to make it work the way we expect. They tend to be compatible with all the other stuff before. We just see new problems, we don't see old recurring problems, but running one flow will not cover the entire space. Every time you run a flow, there'll be a surprise and you have to go deal with it. The timing flow that we have here is a proof of concept, not a production flow today. If we do this, what would it take and how can we go do that? We are working towards productizing this flow, but the data I shared today is proof of concept data, not production data. BCS is production. What it does demonstrate is we can take an existing flow that runs on-prem, and today it's not a huge effort for us to transition it running on the cloud with the environment that we have today. There is a lot of work to enable that to happen, but once you've got there, moving flows up is really typically aligned with what you would qualify. When you make a big change to a flow, you have to requalify it. It's of that order in terms of requalifying Amazon as to when you do a signal enhancement in the flow in terms of the retesting process. There's not any additional work beyond that type of validation. And I do want to say thank you to TSMC for letting me do this. Synopsys for allowing me to run all their tools on the cloud and making that process straightforward, both from a support perspective. They're doing a lot of work on debugging binaries and giving me updated binaries to make things work better on the cloud than they did before. So kudos to them for actually putting their toe in the water with R&D and making things work better than the initial runs did. Amazon themselves for giving me a cloud environment that works. ICManage for giving me all the PeerCache stuff. And Xilinx for letting me go do this stuff because it's fun and exciting. I enjoy doing it.